So in the previous video, we talked about how Rolle's theorem was a special, it was a special case of the mean value theorem. So the mean value theorem generalizes Rolle's theorem. In other words, it takes it and backs it up a step. One of the key components to Rolle's theorem was that f of a had to equal f of b. So what happens then if f of a doesn't equal f of b? Well, if f of a and f of b are different y values, right, then we have a shape that looks more like this as opposed to one that looks more like this, okay? So our ability to guarantee that horizontal tangent line goes away now because I could connect these 2 points with just a straight line. So I don't really know that there's a curve like this. It could be that there's just a straight line. If these values are equal, I know that it has to go up and come back down. Or I know that it can connect with just a straight line like this, but even in that case, the slope of that line is 0. So when we talk about mean value theorem, we're going to generalize this and we're going to say, okay, if f of a and f of b are not equal, right? They're not equal. Then our picture looks more like this as opposed to this, which changes what statements we can make. Take a look at what we say right here about the mean value theorem. Let f be continuous over the closed interval AB and differentiable over the open interval AB. There has to be at least one point so that f prime of c equals this thing. Okay, now I know we probably didn't spend as much time as we needed to on what this is, but this is the average rate of change. Average rate of change. More generally speaking, this is the slope of a line. F of b and f of a are y values, and b and a are x values. And you know that if you do y2 minus y1 over x2 minus x1, you get the slope of a line. So take a look at what we have here. We've got a, and we've got b, and we've got a line that connects a and b. But this is not a tangent line, it is a secant line. Okay, we talked about this way earlier in the class when we did the definition of a derivative and limits and all that stuff. Now, we're looking at f prime of c, which implies a tangent line slope. Okay, slope of a tangent line. And what I want you to notice is that pink line touches the graph in one place. This one does as well. So what we're saying with the mean value theorem is that the mean value theorem guarantees there is a place where the instantaneous rate of change is equal to the average rate of change. Okay? There's a place where the instantaneous rate of change equals the average rate of change. So we're actually going to use this thing right here. We're going to set our derivative equal to the slope of that line. So when we talk about Rolle's theorem being a special case, the slope of this line is 0. And so we set our derivative equal to 0. All right, so take a look at this one. We know that the square root of x looks like this. Okay. That means it is continuous and differentiable. Get that I in there. Continuous and differentiable. There exists at least one value of c so that the derivative is equal to the average rate of change. So there is a point right here where we have this and we have this, okay? And the line connecting those 2 points might look like this, but then we have a derivative where it touches the graph in only one point. So this is supposed to touch the graph in only one point. And you can see that those lines are parallel. Again, in these problems, we're going to know that we're done when we figure out what c is equal to. Okay. In this case, it says, find the values guaranteed by the mean value theorem. So we've already said that the mean value theorem applies because this is continuous and differentiable. If you plug in 0 for x, you get 0. And if you plug in 9 for x, you get the square root of 9, or 3. Notice that f of 0 does not equal f of 9. So what we're going to do is apply the mean value theorem. And here's where we do that. We take the derivative. Okay, so the square root of x, the derivative of that is equal to 1/2 x to the negative 1/2, or 1/2 square root of x. And that's what they've listed right here. Okay, here's how they got there. We're going to take that derivative and we're going to set it equal to something. Rolle's theorem would say set it equal to 0, but we're not doing Rolle's theorem because Rolle's theorem doesn't apply. We're doing the mean value theorem. The mean value theorem says that we're going to take our derivative and set it equal to the average rate of change. We're going to set that equal to f of 9 minus f of 0 over 9 minus 0. In other words, we're going to have 1/2 square root of x equal to 3 over 9, or 1/3. You can see how if you took this out and cross multiplied, you'd have 2 square root of x equals 3. So square root of x equals 6. Excuse me, doing that, having a little bit of a brain lapse. The square root of x is equal to 3/2, so we're going to take the square root of 3/2, right? So we'll have the c. I've got an x right here. Technically, this should be c, right? Because mean value theorem. Okay, so if you're finding x as the answer instead of c, it's fine. It's not a big deal. But our c value is the square root of 3/2. Now, we're probably not going to like how that's written. There's some algebra that goes on right here. So we would call that the square root of 6/2. Let's see. So they're getting c is 9/4. You know what? I have a bit of a brain lapse, guys, and I want to apologize. You're probably sitting there going, oh my goodness, what is this guy doing? Let me go back here and go through this one more time here. So this is, we're going to have 2 square root of c equals 3. The square root of c is equal to 3/2. To get rid of the square root, I have to square both sides. Sometimes when I'm doing these things, I get a little bit ahead of myself, and I'm not thinking about actually what I'm saying. So I want to apologize to you here if you were sitting there wondering, what is he doing? Yeah, I got to get rid of the square root by squaring both sides. Okay, so that's where we're getting 9/4. Sometimes I have to check myself because the PowerPoints aren't always right, and I want to double check to make sure I didn't mess up. And in that case, it was all on me. Okay, so here's another mean value theorem problem. And I think you're getting the idea on how to do these. I'm going to let you look at a few of these and just kind of see what's up. But what I wanted to do was, before we were done with this video, I wanted to look at a couple of these application problems, okay? So let's take a look at this one. You're going to see these in later homework assignments, but I thought it'd be a good idea for us to go ahead and do them now. Just in case when you get there, you've already seen it once, okay? So this is a problem involving motion. We have a rock that's dropped from a height of 100 feet. Its position t seconds after it's dropped until it hits the ground is given by this equation here. So this equation, S of t equals negative 16t squared plus 100 is the position of the object, okay? That's the position. Now, there's something about this. It says that the rock was dropped. And because we say that the rock was dropped, there's an implication we make. It's that the initial velocity is equal to 0. When I drop something, I'm just letting go. So to begin with, there's no force given to it. The object simply starts from 0. we want to know how long does it take this rock to hit the ground. So in other words, I want to know when is the position equal to 0. In other words, I'm just going to set 0 equal to negative 16 t squared plus 100. I'm going to move 100 to the other side. And then I can divide both sides by 16. So I get t squared equals 100 over 16. If I reduce that, I can divide them both by 4, right? T squared is also equal to 25 over 4. Now I'm going to take the square root, right? So the square root is going to be plus or minus 5 over 2. I think everybody's going to be able to see that we're talking about a time value, and a negative time value really doesn't make sense. So if we were to answer the question, how long does it take before the rock hits the ground? It's 5 over 2 seconds, or 2.5 seconds. In the next question, we talk about finding the velocity, the average velocity of the rock. Okay, when it's released and when it hits the ground. Okay, so in other words, the average velocity of the rock over this time interval. So we just figured out this time interval was 0 to 5 over 2. So to find out what the average velocity is, notice that we're plugging 5 over 2 and 0 into s, right? Here's something that you need to know. The average velocity is equal to the change in s over the change in time. We refer to the change in s as the displacement, okay? The displacement of the object. The change in position, right? That's change in position. So to figure out the change in position, we're just going to do s of 5/2, which we know is 0, minus s of 0. Okay, so we're plugging 0 into the original equation. Remember, the original equation looked like this. So this is going to be 0 minus 100 is negative 100. And if you do the math, right, negative 100 divided by 5/2 is going to be negative 40. Now, here's the thing I want to point out to you. You notice that the average velocity is negative. That negative indicates that the object is moving down. Object is moving down. It could also indicate that the object is moving to the left, right? Because left and down are negative directions. So our average velocity is negative 40. Now, in the third question, they say, find the time t guaranteed by the mean value theorem when the instantaneous velocity of the rock is the average velocity, right? It's just a fancy way of saying set the derivative equal to the average velocity. So our average velocity is this, and we're going to have to set the derivative equal to that. So if I take the derivative of negative 16 t squared minus 100, that derivative is negative 32t. And I'm going to set negative 32, so it's C that we're looking for, right? C is that letter guaranteed by the mean value theorem. And setting negative 32 equal to negative 40 and solving for C, we get 5 over 4 seconds. So here's our closing statement. After 5/4 of a second, the instantaneous velocity equals the average velocity. Now, remember, the average velocity is just how fast is that thing moving on average, okay? So we know that in the very beginning, the velocity, the rock is just sitting there. And so if I were to indicate the rock's motion with arrows, the velocity is very, very small to begin with. But what happens to the velocity over time? It continues falling. Imagine if someone had just a rock or a ball, okay, and they were to drop it on your head, just holding the ball over your head, maybe, I don't know, maybe 6 inches, okay? That's not going to hurt that bad. It's an ouch, but not that bad. But if we have the same situation, okay, where we have an individual holding a ball over your head on top of a building, right? Maybe the Empire State Building, and they drop it off that building and it falls 600 feet, right? that's going to be a much bigger ouch, okay? So the point is, over time, the velocity of that object is increasing. Negative 40 is just what that velocity is on average. The derivative would give us the velocity at any point in time, which would not necessarily be negative 40. There are a couple of other problems where we look at the same type situation, and they're worth going through and looking at some of these problems. Just some application problems, and this one is the average rate of change of production of chocolate bars. My wife's a big Snickers fan, so she would be interested in that problem. Here's one. So if we take a look at it, it says differentiate this function. What can you say about f of x over the interval from negative 3 to negative 1? So this says f prime of x is greater than 0 for all values in the interval, negative 3 to negative 1. Thus, we can say that f of x is an increasing function of negative 3 to negative 1 by corollary 3 of the mean value theorem. Okay, so I know you're probably sitting there going, what on earth is he talking about? Well, this is laying the foundation for some things that you're going to see in the next video, where we talk about the first derivative test, okay? So really and truly, what we say about negative 3 to negative 1 is, if I look at the derivative at negative 3, what is the value of the derivative at negative 3? Well, that value is going to be not 54 minus 6 minus 2, okay? And then if I look at the value of the derivative at negative 1, f prime of negative 1, 6 times negative 1 squared plus 2 times negative 1 minus 2. So here we have 6 minus 2 minus 2. The derivative in both of these instances is positive, okay? So if both the derivatives are positive, if f prime of negative 3 is greater than 0 and f prime of negative 1 is greater than 0, is it possible for f prime of negative 2 to be equal to 0? Is that a possibility? Well, because of the intermediate value theorem, we can say no. It's not going to be. I can't guarantee that it will be. Okay, I can't guarantee that the derivative of negative 2 would be 0 because both of these are positive. So again, I don't think you're going to see any homework problems necessarily on this. This is just kind of laying the foundation for what we see in the first derivative test, okay? And there's some others here. Again, most of the problems you're going to see in the homework that you do is going to be those problems where you have to find that value of C, okay? I do apologize for the length of the videos here. However, I think it's worth going through and seeing these worked out, because there are some things that are helpful to know that you don't necessarily see in those PowerPoints. As always, please reach out. Please let me know what I can do to help you as you go through these problems.